So today's lecture is on machine learning. We are building on our previous topic, which was Bayesian inference, by discussing perceptrons and logistic regression. Now, the topic of today begins with a discussion on linear classifiers. Remember last time we learned about learning probabilistic models. We called that approach, or we categorized that approach under the class of model-based machine learning, which meant that we explicitly learned a probabilistic model. We learned the distributions, joint probability distributions of the data and the labels, and we made our inferences based on the learned model. What we're going to talk about today is a bit different. We are diving into a new category of machine learning algorithms called model-free machine learning, in which we do not explicitly learn the probabilistic model, but we make our inference through a different form of function approximation. In the beginning, as I mentioned, we are going to start on linear classifiers and we'll build on it as we move forward. So, remember, like last time, similar to last time, we are dealing with the problem of figuring out a label for an input X using a model that works on a feature representation of X. So one of the examples we've been using in our machine learning lectures was handwritten digits recognition. We have this image of a handwritten digit, let's say 2. We have the feature representation through, let's say, individual pixel values, as well as a few other handcrafted features, such as number of loops in the image and so on. Now, what we're going to focus on today is going to be this part here. How do we get from this feature representation to this label? Now, our discussion is going to be very loosely based on how a human neuron works. So you're probably familiar with this schematic. You've probably seen it in your school year's biology lessons. This is a neuron comprised of dendrites, which are input connections or input interfaces to the neuron. Each dendrite receives a signal from its connections to other neurons. It can be from, for example, the retina in your eyes. And then these signals are all amalgamated and integrated in the body of the neuron and are modulated in some way, and their output flows through an axon. So axon is like an output channel for a biological neuron. This axon is then connected to the synapses, which are intermediary bridges between this output and the input of other neurons. Okay, this seems very complicated and intriguing at the same time, but for the purposes of our work, let's see if we can come up with a simplified model. This is what is typically called a circuit level abstraction of a neuron. So you will see that the dendrites are modeled by input channels. Each input value or each input stream is then modulated, in other words, multiplied by some weight. This is like a factor multiplied by the input. Now, all of these inputs multiplied by their weights are then summed up in the body of the neuron. And then the summation goes through some sort of activation, and the output is generated and it flows through the output channel. This is a very simplified model of how a neuron works. It's not accurate at all. So you can't think of your biological neurons acting in this way. The dynamics and the behavior of a biological neuron is significantly different from this model. However, as I mentioned, this model is a very simplified operational or functional abstraction of this model here, of the actual neuron. Now, in linear classifiers, we call this a perceptron in a linear classifier. This model is called a perceptron. The inputs are the feature values. So each feature value, like in the case of handwritten digit classification, each pixel value goes through one of these input channels. So the first pixel value can go in here, the second pixel value can go in here, and so on. Each feature has a weight, which is this component here. And then the sum of all of these is called the activation, or what comes out of the perceptron. So in mathematical terms, the activation for an input X, like an image X, with weight W, is given by the summation of each input feature. So X is comprised of a number of features. We're representing X with a number of features, like F1 of X, F2 of X. Each feature multiplied by the corresponding weight, the weight of that feature, the weight of the input channel dedicated to that feature. Now, this summation can also be formulated as a dot product. If you recall dot products from your earlier linear algebra classes or calc classes, this is essentially the same thing. So this summation is what comes out of this neuron, we call that activation, and can be represented as a dot product between a weight vector, a vector comprised of all of these weight values, WIs, multiplied by the feature vectors. So the vector composed of all of the feature values of X, our input sample. Now, let's look at the simple case of binary classification. Let's say we want to do a spam or ham detection. If the activation is positive, if the value of the activation is greater than 1, we can say that the output is +1. So if it's a spam detector, the output will be, yes, it's a spam. If the activation is negative, then the output is not spam. And this is only for the case of binary classification. And this is another way of representing the same thing. So we have feature values, each multiplied by a weight assigned to that particular feature. Remember, I'm saying this weight is for that particular feature, not that particular feature value. So we're saying, for example, the number of occurrences of the word by has a weight of 2. We are not saying that 2 occurrences of word y has a weight of 2. We're saying any value that comes for f1 is going to be multiplied by this w1. And then we sum these up, and in the end, to make a decision, we just say if it's positive, then it's +1. If it's negative, then it's -1. Now, understanding this is really important. So we're going to build the rest of this lecture and our discussion on this formulation. Does anybody have any questions about this formulation? Is it clear, or does anybody have any doubts or comments to make about this one? Very well. So let us continue. Now, let's talk about weights. In the binary case, we are essentially comparing features to a weight vector. What does that mean? Let's say we have this weight vector here. So the number of times the word free has occurred can be 4. The number of times your name is in the text of an email gets a weight of -1. And again, we are, just a reminder, we are talking about a spam classifier. If there is something misspelled, it gets a weight of 1. If the email is from a friend, it gets a weight of -3. Okay. Now, let's say we get a sample x1 with this feature representation, with this feature vector. So the value of free is 2. Your name, there is no mention of your name in the email, so it's 0. How many misspelled words are there in the text? 2. Is it from a friend? No. And if we multiply this feature vector by w, what do we get? What's the dot product of this vector by this vector? It's 2 times 4, which is 8, plus 0 times -1, 0, 2 times 1, 2, 0 times -3, 0. So it's 2 plus 8, 10. If the dot product is positive, it means that this belongs to the positive class. What is the dot product? It's 8 plus 2, it's 10. So this input sample x1 belongs to the class spam. That's our positive class. Let's look at this one here. So we have an email x2. Its feature representation is as follows. It doesn't contain the word free. The number of times the word free has occurred is 0. It does contain your name, so 1. There is 1 misspelled word there, and it is from a friend. So let's see what the dot product of f of x2 by w is. It's 0 times 4, so 0 so far. 1 times -1, so far we have -1, plus 1 times 1 plus 1, plus 1 times -3, which is -3. So if you sum it all up, you'll see that the dot product of w by fx2 is actually -3. It's negative, so it does not belong to the positive class. It means that this sample is not going to be classified as spam. Any questions? Very well. Now, let's talk about decision rules. How do we decide on the boundary between positive samples and negative samples? In other words, how do we decide between samples that belong to the positive class and the samples that belong to the negative class? Now, imagine the space of feature vectors. Remember, this is an AI class. So when I talk about space, I'm not talking about outer space. In this class, the word space refers to a set, or let's say a multidimensional representation, a vectorial representation. Now, in the space of feature vectors, each sample is a point. So let's say it's a two-dimensional space. Each of our samples is a point on this plane. Any weight vector is a hyperplane. What's a hyperplane? You should already be familiar with this term. But in here, we're talking about a plane perpendicular to the original space of feature vectors. In binary classification, one side of the hyperplane, or the weight vector, corresponds to the positive class, and the other side corresponds to the negative class. So let's say we are representing every email with two features. The number of times the word free has been used in the text of the email, and the number of times the word money has been used in email. Now, the weight vector can be represented, the hyperplane, or the decision boundary for the weight vector, can be represented as such a division. We can say that anything that falls on this side of the weight vector is ham, and anything that falls on this side of the weight vector is spam. Now, here's a fundamental question. So far, we've talked about the formulation of the perceptron model, or linear regression model. Venkatesh, do you have a question?
No, Professor, sorry.
It's all right. Now, so far we've talked about the formulation, we've talked about the meaning of weights, we've talked about the meaning of feature vectors, and we've talked about the activation, we've talked about decision making, and so on. Now, just to make sure we are all on the same page, what do you think the learnable parameter in this formulation is? What is it that we need to learn? Is it f of x? Is it the activation? Is it the W vector? So how many of you believe that the learnable parameter is the activation? Show of hands. How many of you believe that the learnable parameter is the feature vector? Okay, 3 people. How many of you believe that the learnable parameter is the weight vector? Nobody? Okay, I'm really happy that I asked this question. The correct answer is the weight vector. So typically, in a machine learning problem, we already have the samples and the representation of those samples. That's f of x. And what we want are weights that allow us to make correct decisions. These weights are not known beforehand. This is the parameter that we will be learning. This is why Perceptron is a machine learning model. We need to find the weights of this perceptron to be able to come up with activation values that make sense, that are able to correctly classify the values for us. Does that make sense? Any questions about that? All right. Let's continue. Now, how do we learn the weights? Well, so far we've seen a few learning approaches. We've seen iterative learning of value functions and Q functions in reinforcement learning. And we've seen sample-based learning of naive Bayes. Now, for binary classification using Perceptron, we can follow a similar procedure. And what's that procedure? Similar iterative procedure. The procedure tells us to first initialize all weights to 0. Then, for each training instance, for each new sample that we want to train on, classify with current weights. So feed the sample, the feature vector of that sample to the perceptron and see what decision it makes. If the decision is correct, in other words, if the output is the correct output, and we are going to represent the correct output with y star from now on, then there's no need to change the weights. So far, the weights are working for us. However, if the output is wrong, then adjust the weight vector. How do we adjust the weight vector? And first of all, how do we know that the output is wrong? How do we measure this? Does anybody have any thoughts on this? Ramu?
When the weight comes under the ham section.
Well, how do we know?
By calculating, like previously we have a graph, right? Before the vector, it will be a ham. Like if the value is the weight. Oh, I'm sorry.
It's okay. It's okay. That's not the answer I was looking for. It's a little more detailed than what I'm looking for. Satvika, would you like to share your answer with us?
Compare with the predefined values.
Yes, that's exactly what I was looking for. Thank you. So the samples that we are training on in the settings of binary classification, in the settings of supervised binary classification, all come with correct labels. So while training, we have, for example, an email in our training data set. In the training sample set, we have an email, and we have the correct label for that email. We have for example, for an email, we have a label that says this email is a spam. And then for another sample, we have the email and the label that is ham. This is how we see whether the output of the model is right or wrong during supervised training. This is why we call this class of machine learning supervised learning. Why? Because there's a supervisor, there are those predefined labels that check to see whether the output is right or wrong. Okay, now, if the output is correct, there's no need to change the weight, but if it's wrong, we need to adjust the weight vector. But how do we go about adjusting the weight vector? So in the binary case, again, I'm reformulating what we had before. For each training instance, we classify the current with the current weights, and the output of the classification is going to be a y, which is either +1 or -1. It's +1 if the dot product of the weight vector with the feature vector is greater than or equal to 0, and it's -1 if the dot product is less than 0. If correct, no change. If wrong, we adjust the weight vector by adding or subtracting the feature vector. When do we subtract? If y star is -1, if the correct label is a negative class. So in other words, the new weight vector, the adjusted weight vector is going to be the current weight vector, the one we use for classification, plus the dot product of the correct output and the feature vector. Okay, does this make sense? Why are we doing this? Why does this help? Well, we are essentially telling the weight vector that, hey, you need to get closer to where this dot product is lying, right? You are now here, but we expect you to be a bit closer to where this vector is, right? We are adjusting by bringing the vector closer, by nudging the vector, the weight vector, closer to where it should be for the correct class. Now, the question is, does this work? Does this summation work? Well, actually, no. In the general case, it's not guaranteed to work. There are special cases that we have theoretical guarantees for the convergence of this iterative algorithm. Remember, this is essentially a for loop. We are saying for each training instance, loop over all of the training instances. For each of those training instances, do the classification. If incorrect, adjust the weight. In general, there's no guarantee that we'll get the correct weights, but we'll get closer to the correct weight as we have more samples. Now, we'll discuss this a bit further in the coming slides. Let's look at a quick example. Let's look at a separable case. Remember, the perceptron model is a linear model. So its decision boundary is a line. The model is always going to form a linear boundary. Now, this particular example is very helpful. Why? Because there's clearly a way to come up with a line that perfectly separates the two classes, the positive classes and let's call this the negative class. In the beginning, when everything is 0, for example, we may begin with this training instance, and we may get an incorrect classifier. Then we adjust the weights. We come up with this decision boundary, which incorrectly classifies a particular sample. Then we continue. We adjust the weights again. We come up with another decision boundary of this form, which is obviously not great. If we look at the next training sample, which is this one, we have to correct the weight vector. We have to adjust it based on where it lies, where the positive sample lies. Then we come up with this. Then we come up with this. And then finally, we find a line that for each of our training samples, each of the samples available to us to learn the model, works well. So eventually we found a good decision boundary. What about multi-class problems? Remember, this was for binary classification, right? What do I mean by binary? It means that we have two classes. It's either positive or negative. What happens if we have more than two classes? What happens if we want to decide whether an email, for example, is a spam, related to work, or personal? We have three classes now, and we want to train a model that decides which of these classes a sample belongs to. So if we have multiple classes, then we define a weight vector for each class. So we are going to designate classes by Y. We'll have a weight vector W sub Y for each of these classes. So we'll have W positive, W circular, W negative. Then we score the activation function, the activation of a class Y, which is essentially this dot product. Remember the original definition of activation. It's a dot product of the weight vector and the feature vector of a sample X. So we come up with this score, or this result, and then we say the prediction, the result with the highest score wins. That makes sense, right? So the class that has the highest value of activation is the most likely class. Think about this for a second. We'll come back to this and dive into the details of what I just said a bit more. Okay. All right. So what does this mean geometrically? Previously, our decision boundaries were just hyperplanes based on a hyperplane between two classes, right? How do we imagine hyperplanes or decision boundaries for multiple classes? Well, this is a relatively decent representation. So we can say everything that falls in this region of this three-dimensional space belongs to the second class. Everything that falls in this region belongs to the third class, and everything that falls to this region belongs to the first class. And of course, it's intuitive. It follows that binary classification is essentially a specific case of multi-class classification where the negative class has weight 0, right? So the classes that don't matter, the other class, the negative class, is always multiplied by a weight vector comprised of all zeros. This is mathematically helpful, right? It helps us see how we can apply everything that we learned about multi-class decision rules and multi-class classification to binary classification as a specific case. Any questions so far? All right. So how do we learn the weights for multi-class perceptron? It's similar to what we did for the binary case. We start by initializing the value of all weights to 0. Then we iterate over all training samples, every sample that we have in our training set. For each of those training sets, we predict the output with the current weights. So what's the output? We find the dot product of each of the weight vectors. Remember, if you have 3 classes, we have 3 weight vectors. If you have 4 classes, we have 4 weight vectors. If you have 2 classes, we have 2 weight vectors. So actually, if you have 2 classes, we do have 2 weight vectors, but the second vector doesn't really matter because it's all zeros. So we calculate the dot product of each of the weight vectors and the feature vector. And then we will say the output is the maximum value that we get among those 3 or n calculations. Let's say we have 3 classes. Let's say we have 3 classes. So we do W1, the weight vector for class 1 multiplied by f of x, W2, the weight vector for class 2 multiplied dot product with f of x, and W3 dot f of x. Then we'll see which of these, the values of these dot products is the largest. And then we'll say the class that produced the largest value is the prediction of that model. So if the first class, if the dot product of the first class and the weight vector for the first class and the feature vector is the largest, we are going to say the correct, the output of the model is the first class. Now, if correct, if the output is correct, if y is actually the same as y star, there's no need to change the weights. So far, the weights are working for us, doing what we want them to do. If wrong, we lower the score of the wrong answer and raise the score of the right answer. What does that mean? So this is the weight vector of the wrong answer, the weight vector of the incorrectly predicted class y. W sub y is adjusted by decreasing its score. In the simplest form, this reduction or lowering of the score is in the form of just subtracting f of x from it. Remember, these are all vectors, so these subtractions are vectorial. And then we raise the score of the right answer. The weight vector of the correct class is then increased through this vectorial addition with the feature vector. Does this work? Again, in general, no, there are no guarantees that it will converge to the optimal answer. But in general, the more iterations that we have, the closer to the optimal answer our model becomes. You should be full of questions at this point. Does anybody want to ask anything about what we've covered so far? Are we clear on what these parameters are? Satvika?
If I have a question regarding this adding to the right answer, raising score to the right answer. Like if we get the right answer, then why we need to raise the score of the right answer?
Well, if we get the right answer, we don't change it at all. However, if we get it wrong, it means that instead of getting class Y star, we are getting class Y, right? This tells us that the current weight vector for class Y is biasing the answer too much towards class Y, so we need to decrease that emphasis. And it means that the weight vector for the correct class, Y star, does not have enough emphasis towards class Y. So we increase that emphasis by through the summation. Does that answer your question?
Yeah.
Are you sure? You still sound a little doubtful.
Like if we actually it is for one class, it's the correct answer, right? If it's correct for one class, then why to raise that weight for that correct class?
What do you mean? Shall we discuss this in the context of an example? Let's say we want to train an email classifier with 3 classes. Class 1, spam. Class 2, work. Class 3 is personal. Okay? Now, during training, we pick up a sample. Remember, the samples in supervised learning are essentially the contents of an email. Let's say the feature representation of an email. I'm going to call it email 1. And the correct label. Let's say email 1 is work related. Actually, just to make sure we don't get into notational confusion, I'm going to say this email 1 is a personal email. This is what we have in the training set. Now, when the training loop gets to the sample, it picks up the feature vector, f of E1, multiplies it by the weight vector of each class. So it multiplies it by W spam, the weight vector of the spam vector of F, then multiplies it, and by multiplication I mean dot product here, with the weight vector of the work class and the output and the feature representation. And the same goes with WP, the weight vector of the personal class dot producted with the feature vector. And all of these are just f of E1. I didn't write that here. Now, let's assume that the prediction for this sample comes to be spam. So Y is S. This is wrong, right? How do we know it's wrong? Because we know the correct label, the correct class is P. Now, what we are going to do to adjust our model or nudge our model towards a correct classification of this sample is First, we say there is too much emphasis on the span class for this feature vector. So let's reduce that emphasis through this reduction. We also say that the weight vector for the correct class P is also not sufficiently emphasized on. It's not sufficiently advocating for the correct class. So we adjust for that by incrementing it by the feature vector. Now, is this always correct? Are we always going to get the correct result after this adjustment? No. This is an iterative process, remember? Every time we do this adjustment, we get a little bit closer towards where we want to be, where we want the weight vectors to be. Over time, some iterations may actually, the adjustments in some iterations may actually go a bit further from where the optimal answer is. But over time, on average, this adjustment is going to get us closer to a good estimate of the correct weight vectors. Satvika, I know that this may not have been the answer to your question.
With this example, I got it, Professor.
All right. Now you seem a little more confident. That's good to hear.
Yeah.
Any other questions?
No.
Very well. Anyone else? Any other questions from anyone else? All right. Let's continue. And Satvika, thank you very much for asking that question. I want all of you to know this. If you have a question, if something is not clear to you, chances are almost everyone in the class is dealing with the same confusion and problem as well. So don't be afraid to ask questions. Now, let's talk about some of the properties of perceptrons. If the training set allows for a linear decision boundary that perfectly divides the samples between each of its sides, we call that training set linearly separable. So separability is when there is a linear boundary, there is a linear decision boundary that perfectly divides the samples into their correct classes. Is that always true? Well, actually in practice, separability is very rare. We often have data sets that are like this. It may be impossible for us to find a linear decision boundary that perfectly divides the two classes. Now, why did we define separability? Because it allows us to study the case of the problem of convergence. Does the algorithm, the training algorithm, that iterative algorithm that we talked about, necessarily converge? Well, it turns out that if the training set is separable, the perceptron will eventually converge. And this is guaranteed only for the binary classifier with separable data. Now, does that mean that we can't use perceptron for non-separable data sets? Well, you can. It's not going to be perfect, but it may still work well enough for your problem case. How do we know how well it can work? Well, we can actually measure the mistake bound, the upper bound for the number of mistakes that the model can make using this boundary formulation. What does it say? It says the maximum number of mistakes in the binary case are related to the margin or degree of separability. What do I mean by degree of separability? The degree of separability is essentially a measure of how far the closest element of each class is to the decision boundary. So the distance between this instance and this decision boundary is called delta, or the margin. What's K in this formulation? K is the number of features. So this formulation is essentially telling us that the number of mistakes, or the measure of mistakes, is upper bounded by the ratio of number of features over a square of the margin, or degree of separability. How do we interpret this? It's telling us that if the degree of separability is large, the larger the degree of separability it becomes, the smaller the number of mistakes becomes. However, if the separation between two classes is not that much, if the classes are very close to each other, the decision boundary is leaving a very narrow margin for each classes, then this value becomes smaller and this bound becomes larger. So more mistakes can be made. What about K? Well, this is also interesting. It's telling us that the more features we have, the less the less prone our model is to making mistakes. So it's better to models with, or feature representations with more features, in the case of binary perceptrons, are less prone to mistakes than those with fewer features. Does this make sense? Why does this matter? Why would we want to consider this? Why did we spend so many minutes on interpreting and discussing this formula? It's telling us that the number of mistakes that a binary perceptron can make is not infinite, it's bounded. And if we choose the features wisely, if we have a rich representation, which means if we have a good number of features, and if the margin in the training set is small, then the performance of our model is better than the performance of our model is bounded by this number of mistakes, which means that we can still apply binary perceptron to non-linearly separable models with an expectation of performance within this bound. Does that make sense? So this is essentially justifying the use or adoption of binary perceptrons for real world problems. This is telling us that the number of mistakes that those models can make are bounded, they're not infinite. So there's a limit to how many mistakes they will make, which means that we can still apply those models in practice and expect a limited number of mistakes to be made, which is acceptable in machine learning in general. What are the problems with the perceptron? Well, the first problem we're going to talk about is noise. If the data is inseparable, weights may thrash around during training. So weights may keep going left, right, this way, that way during training. But averaging weights, the weight vectors over time can reduce this thrashing, this erratic adjustment of weights. Another problem is mediocre generalization. The perceptron model finds a barely separating solution. It leaves a very narrow margin between the two classes. So what does that have to do with generalization? Remember, the idea in machine learning is to learn something, learn a function like a decision boundary from limited samples that applies to unseen samples. That's called generalization, right? Imagine that we have this decision boundary between these two classes, and imagine we train our model, we come up with this decision boundary for this particular class. What happens if our next blue sample falls here? Then this is outside the decision boundary of the blue class, and it may be misclassified as red, right? The fact that there's very little room for variation on this side, and again, very little room for variation on this side as well with regards to these decision boundary, means that there isn't much room for generalization. There isn't much room for samples that still belong to this class, but maybe a little outside of the decision margin or the decision boundary that we've come up with. Okay, so this is a problem. And a related problem is overtraining. We've already talked about overfitting. So with perceptrons, actually this may actually apply to many other and more advanced machine learning models. We typically have a test and held out or validation set. We've already talked about this. We use the validation set to tune our hyperparameters, and we use the test set to measure the performance or accuracy of our model. Now, accuracy usually rises during training and then falls. Why does this happen? Do you see what's happening here? It keeps rising, the accuracy on the test set and the held out set, and then it starts falling. This is called overtraining. We've found a perfect model here. We've found the perfect hyperparameters and the perfect model parameters at this point. But then, since convergence is not guaranteed, if we keep training past this point, we keep adjusting the weights and parameters to something other than perfect, and that's why the performance falls after this point. So typically, we let the training algorithm run for many iterations. Then we plot this or a similar graph, and then we check to see what the model parameters and hyperparameters were at the point of saturation, and we say this is the model that we want to work with. Okay, Before we start our discussion on logistic regression and improving perceptron, does anybody have any questions? All right. So let me see. Very well. I'm going to continue for a few more minutes and then we can have a short break. Now, how can we improve the perceptron model? Imagine the non-separable case and the fact that we want to come up with a decision boundary. In the non-separable case, even the best linear boundary makes at least one mistake for this case, right? Why? Because there is one sample of the positive class that falls well beyond any linear boundary that can be found between these two classes. But what if we were to go with a probabilistic decision boundary instead of a deterministic boundary? What if we were to come up with probabilities of how likely it is for something to be on one side and the other side, instead of saying that everything that's on this side is positive and everything that's on this side is negative? That's called a deterministic boundary. What if we could come up with a probabilistic decision boundary? So let's say we have this probabilistic boundary, meaning that everything that falls on this side, on this line, has a 50% chance of being red and 50% chance of being blue. To make it more clear, let's look at another example. Everything that lies on this line has 30% chance of being red and 70% chance of being blue. Let's look at another example. For this probabilistic decision boundary, everything that falls on this line has a 70% chance of being red and 30% chance of being blue. Let's look at one more. Everything that falls on this line has 10% chance of being red and 90% chance of being blue. These are examples of probabilistic decision boundaries. Okay. Well, what can we do with this notion? How can we make use of it? Well, remember the scoring of perceptrons? We said the score for each perceptron is essentially the dot product of the weight vector and the feature vector. If the score was very positive, then we want the probability of the positive class to be closer to 1, right? Like if the value of z is, let's say, 12 or 20, we want the probability assigned to this class being positive to be closer to 1. Remember, probabilities are between 0 and 1. If it's very negative, we want the probability to be closer to 0. The probability of this sample belonging to the positive class to be closer to 0. Now, we have a problem here. The probability values are between 0 and 1, right? Right? So probabilities are always between 0 and 1. However, these scores are all over the place. They are not bound by being between 0 and 1. How can we convert real values, real scores? How can we map these scores to a value that falls between 0 and 1. You've probably already seen this in the course. There's a very good solution for it, and that's a sigmoid function. Remember the magical sigmoid function? For any value z, the sigmoid function maps that value into a value between 0 and 1. And it's a relatively simple function. It's just 1 over 1 plus e to negative z. For those of you who don't remember, e is a mathematical constant. All right. Now, given the probabilistic mapping of scores to probabilities, or given this formulation of probabilistic decisions, how can we find the best W's? Well, we've already seen a method that helps us find the best W. We saw it last week. It's a maximum likelihood estimation method. So remember maximum likelihood for naive Bayes. In here, we want to find a maximum likelihood formulation that helps us find the most likely W's, the most likely weight vectors, or the weight vectors that maximize the probabilities of the correct classes. So we can formulate it as the maximum over the maximum over W of this summation, this log of the probability of each class being the correct class given the feature that we're dealing with, a particular feature, a particular sample. This is the feature representation of a sample, considering that the weights are W. Now, this is very cryptic. Let me break it down. We have I samples in our training data set, right? Each sample is the feature representation of an email and the correct label. Now, essentially what we are doing in here is we are calculating the probability for each sample. We are calculating the probability of a class, of the correct class for I occurring given xi with a model that uses W. If you have the W, it's really straightforward to calculate this, right? We just predict the output of each X. We get a corresponding Y, and then we calculate it. Now, what we're looking for in here is the best W, the W that maximizes the probability of the correct class for Y. So how do we break this down? We can break it down by saying, in the binary case, that P of Y super I being the positive class given the sample and a particular weight vector is essentially the sigmoid of the activation. 1 over 1 plus e to negative w dot f of the feature of the feature vector of the sample. This is essentially turning the score of this sample into a probability. What about the probability of the negative sample? Well, in the binary case, we only have two possible outcomes. It's either the positive class or the negative class. We've already calculated the probability of the sample being in the positive class. So the probability of the sample belonging to the negative class is going to be 1 minus the probability of the sample belonging to the positive class. Okay, very well. This formulation and this type of machine learning modeling, probabilistic perceptrons essentially, is called logistic regression. And in general, I want you to keep in mind when you see the term logistic, we are often referring to, in machine learning, we are often referring to the use of a sigmoid kernel or a sigmoid mapping at some point. All right. I know that it may be too much. Let's look at a quick example. So we have, let's assume we have a separable case, and we want to make a deterministic decision. We don't want to go with probabilistic models. We want to come up with a line that says whatever is on one side of me is positive and whatever is on the other side is negative. The problem is we can come up with many, many different lines that separates these two linearly separable classes. Which one is best? Any thoughts on that? What are the desired properties of a deterministic decision boundary? Any guesses? How do we know what should be desired? Well, we want our model to make the least amount of mistake, right? Remember this? With regards to the choice between decision boundaries, we have no control over K, but we do have a control over the separation. We want the separation or the margin that the decision boundary leaves for each class to be as large as possible to lower the limit of the number of mistakes that can happen. So that's one of the main properties that one of the desired properties of a good decision, a good deterministic decision boundary. However, let's think about the probabilistic decision boundaries. Which of these two solutions do you think is better? Any thoughts? Ramu?
Yeah, both are same because the probabilistic decision values are same.
Exactly. The decision values are the same. However, the outcome is not the same, right? Look at this bit here. This is lying very close to this line here, which says it's 50% likely to be red and 50% likely to be blue. And in here, we have a 30% chance in between. We have a 30% chance of things being a red and 70% chance of things being blue. So the probability of this sample being red, which is incorrect, is actually not great. we are giving it a relatively high probability for this sample to be blue. But what about this one here? For this one here, the decision boundary, the positioning of the decision boundaries is more concrete. We don't have to deal with giving high probabilities to classes that we know are not going to happen. So this is a more clear and more preferred solution in terms of decision boundaries compared to this one. Let's dig a bit deeper into that by looking at the case of multiclass regression. We have about 20 to 30 more minutes to go. Do you want to take a 5-minute break and then continue? Well, let's take a 5-minute break and come back at 3:15. All right, so we were talking about probabilistic decisions and the formulation for logistic regression, which is essentially the perceptron with probabilistic decision boundaries. And now we want to see how we can extend the formulation of binary logistic regression into multiclass logistic regression. What do I mean by multiclass? Again, I mean that we don't have a it is something or it is not kind of problem. We have multiple possible categories that we can classify our input values in or input samples in. Like the case of categorizing an email into spam, work, and personal. This is a 3-class classification problem. And once again, we are still talking about supervised learning, which means that the samples available to us already come with the correct labels. So we have an objective way of measuring whether the model is doing the right thing, whether the model is making the correct prediction or an incorrect prediction. Okay, so multiclass logistic regression. How do we go about extending logistic regression into the multiclass domain? Remember Perceptron and what we did with Perceptron? We said a weight vector, each class is going to have its own weight vector. We'll have, for example, W spam, W work, and W personal. Then we calculated the score of each class, essentially by doing the dot product of the weight vector for that class and the feature vector of the sample we are looking at. And then the prediction with the higher score wins, which means that the output of the classification model is going to be the class which gets the highest score. That was for multi-class perceptrons. Now, how can we make scores into probabilities, right? If we want to adopt the same approach in logistic regression, somehow we need to convert these scores into probabilities to be able to come up, to be able to use the logistic regression concept here. How can we do this? Well, the sigmoid function already answered that question for us, right? We know how to convert a single score like W spam multiplied by a particular feature vector into a probability. We just put it in the sigmoid function. So we'll come up with 3 sigmoid outputs, 3 scores for 3 classes, spam, work, personal. These are the numerical scores. And then we apply the sigmoid function in this form. What does this mean? Remember the original form of the sigmoid function? Let me go back to that slide. This is the sigmoid function. Now, in the final scoring of multiclass perceptron, we are not only considering the score, the sigmoid of the score for Z1, but we are essentially calculating the sigmoid of Z1 over the sum of sigmoids of all other classes. Why? Well, we want to get the relationship in terms of the ratios of the original scores to be captured in these scores. What's happening here? What's essentially happening is, first of all, these values are all non-zero. And second of all, this formulation ensures that the probabilistic value that we get in here is still maintaining its relationship, its ratio to the other scores generated by our model. Okay, so in other words, these are the original activations, and this is a term that those who've learned about deep learning before are very familiar with, is called softmax activations. Each of these is a softmax activation. Why is softmax important? For those of you who've seen deep learning, you may already who've delved into deep learning or dabbled in deep learning from online courses or other courses, you may know that one of the effects of the softmax formulation or the softmax activation is the smoothing of these values. Later on in the recorded lecture, you will see that this formulation is also very helpful for computing derivatives when we want to find the optimal value of W. Let's see how we can use this formulation to find the best W. Well, again, we want to apply the maximum likelihood estimation in the original form. So we want to find the W that is most likely given the data points available to us. What are the data points available to us? The training samples and the corresponding labels. Now, in this formula, our probability term is given by the softmax activation function. So this is essentially the same as this down here, this one, this ratio down here, where we've plugged in the value of Z, where we get the value of Z instead of Z. So this is Z of xi, and this is the softmax function applied to z of xi. All right. This is all we need to formulate the maximum likelihood estimate of the best W for multi-class logistic regression. There are a number of fundamental issues that I have not talked about. I'm curious to see if anyone has picked up on what's missing in the discussion we've had so far. For that, I'm going to simplify the question to, does anybody have any questions? I know the answer is yes. Is this clear to everyone? Is it clear why we are using softmax activation? Venkatesh?
Professor, I didn't understand regarding the k real numbers, but I didn't find any real numbers we are using here. But why we are using softmax function?
I got the last part of the question. What was the first part?
Real numbers, Professor.
Real numbers, you mean the z values, the scores, right?
Yep.
So we want to convert these scores into probabilities that can be compared with each other, right?
Yes, Professor.
For comparison purposes, we need to be able to keep those probabilities, the ratio of the scores, the scores for each class intact when we convert them into probabilities. To preserve the ratios of those scores when we convert them into probabilities, we don't do just the sigmoid conversion, but we do sigmoid over the sum of the sigmoid of all possible scores, all of the scores in total. Now, first of all, what's the summation of these terms? These all sum up to 1, right?
Yes. Yes, Professor.
So this is one thing that we are preserving here. Remember, the sum of the probabilities of all possible outcomes should be 1. If we had not done this division by the sigmoid of the sum of sigmoids of all classes, there was no guarantee that the sum would be 1. This is very similar to normalization, the normalization trick that we learned about in Bayesian inference. Now, there is another important feature of the sigmoid activation or the sigmoid formulation, and it's the fact that it's very computationally convenient for gradient-based optimization. We'll touch on this in the recorded lecture, in the lecture that comes right after this and in the last few lectures of the course. But as a base reason for why we are using sigmoid as the primary reason, you can say, well, first of all, it allows us to conserve the need for the probabilities to sum up to 1. And second of all, it maintains the ratios of the scores in their corresponding probabilities. Does that answer your question, Venkatesh?
Yes, Professor. But still I'm confusing about the estimating interfaces.
Can you be a little more specific?
But after
You mean?
Yes, Professor.
You mean this part here?
Yes, Professor.
Okay, so again, we want to apply maximum likelihood to come up with W's that maximize the likelihood of the correct probability, right? The correct class. So this is the classical maximum likelihood formulation that we saw last week when we were talking about estimating the parameters of a naive Bayes model. Now, for multi-class classification, we know that the probability of each class, given the evidence, given the feature vector, is given by the sigmoid activation function. How do we know that? Well, this is essentially what we're looking for, right? This is the conversion of the scores into probabilities. What probabilities? These probabilities. This term here is essentially telling us the probability of class 1 being the correct class given the evidence, right? Z1 is essentially the score of the first class, class 1, and this one in here is giving us the probability of that class, of the corresponding class being correct given W. So this is exactly the same as the corresponding softmax activation. How did we get from this to this? Well, from here, we already said that conversion of the scores into probabilities is given by the softmax function. The softmax function was E2Z1 over the sum of all of the sigmoids of the other activations. So E2Z of I is essentially the weight vector of I multiplied dot producted with the feature vector of sample I. That's let me write it down here. This is essentially E2 Z1 divided by, this is the sum of E2 Z1 plus E2 Z2 all the way to E2 Zn, the number of classes. So do you see the mapping between this and this, Venkatesh?
Yes, Professor, but it comes to multi-classes, what we have to do. If it is single class, we will do like this, but if it comes to multi-class.
Ah, I see what the problem is. What is this Y super I? Is this all Ys? No. This is the correct class for sample X super I. So in the training set, what we have is X super I. It's really difficult to write with a mouse, but I'm trying. And the correct label Y super I. In here, this maximization process is essentially telling us we want to maximize the probability of the correct class for sample X super I, right? This is the probability of the correct class for sample I given the weight, a model defined by weight vectors W. So we only calculate this for the correct class, and we want to maximize this probability by choosing the best W. Does that make sense, Venkatesh?
Yes, Professor.
Great, you sound confident. How about everybody else? Is this clear? Is there anything you're not sure about? We have time to discuss. We only have a couple more slides to go through. Shantanu?
Professor, the softmax function does the smoothing process, right? So
Yes.
in our last example of blue and red dots, what exactly does the smoothing will be there? Will it be changing of the values?
No, the smoothing is in the shape of the function itself. Why is it important? Later on in the recorded lecture that comes right after our current lecture, you will see that to solve this maximization problem computationally, we need to calculate the gradient. We need to calculate the derivative of this softmax, right? Of this probability. For us to be able to calculate this derivative, we need this probability. It's much easier for us to do if this probability is a smooth function, a smooth and a continuous function. Why? Because then the calculation of derivatives is much simpler and much more straightforward. If it was something like this, like a step function, then there are points where derivatives explode, right?
Yeah.
We want to smooth the probability out to make sure derivatives exist and are not infinite. You will see that a lot more in the next lecture.
Okay, Professor.
Does that answer your question, Shantanu?
Yes, Professor.
Very well. Anyone else? Okay. I think we only have a couple more slides left. Actually, no. This is our very last slide. Now, in the next lecture, in the recorded lecture, you will learn about how we can solve this optimization problem. I'm just going to give you a preview. As I mentioned before, the solution to this optimization problem is going to be based on gradient calculation. How? Just to give you a brief insight, imagine you want to get to the peak of a mountain, and this is a slightly higher. Let me draw this again. So there's a mountain of this form. Now, some sick people have kidnapped you, blindfolded you, and dropped you from a helicopter somewhere on this mountain. You have a cell phone, but the cell phone doesn't get reception. You want to get to the highest point of the mountain so that you can get some reception. Your cell phone also has this interesting app in it that vibrates when you go up and beeps when you go down, right? So you're blindfolded, you can't see anything. All you have is your cell phone that tells you whether a step you've taken is upwards or downwards. If you are dropped at this point here, and you've lost your sense of altitude, so your body doesn't sense whether you're going up or down. If you're dropped here, well, you first take a random step, let's say to this direction, and then your cell phone beeps. It tells you you've gone down. You know that you want to go up, right? So then you take a step towards this direction. It tells you you're going up. Then you see that this direction is working. You keep going towards this direction until you get to this point, and there isn't much to do. So you do a little bit of random exploration and you follow that pattern until you get to the highest point, right? Gradient-based optimization is exactly like this. Think of the space of all possible solutions for W as a mountain. If W has 3 parameters, it's a 3-dimensional mountain. If it has 2 parameters, you can think of it as a curve, and so on. And what you want to find is the values of W that maximize where you stand in that landscape. You want to get to the peak of this problem. And you are blindfolded and you don't know where you are in this region, but you know that you have to move towards the maximum altitude, where the value of this is maximum. How do you do that? What is available to you to signal on whether you've moved upwards or downwards? It's the derivative of your trajectory. If you move upwards, the derivative is going to be positive. If you move downwards, the derivative is going to be negative. Just a quick reminder, when you're dealing with multivariable functions, let's say you have let's stick with this color. You have a function f of x1 and x2, then the derivative of this function with respect to x1 is called the gradient of the function with respect to x1. And what does this mean? It means that it measures how changes in this parameter, x1, affect the changes in f1. So in the next lecture, you will see how gradient-based optimization, calculating these gradients to figure out whether you need to go up or down, can be applied to solve this optimization problem and finding out W. You will also learn about how logistic regression and the perceptron model can be extended into the neural network model. Right now, you essentially know what a neural network is, you just haven't seen the term. A neural network is, in essence, a cascade or a network of connected perceptrons, or even in the probabilistic case, you can think of it as a network of logistic regression perceptrons. That's all a neural network is. You'll get to learn more about this in the next recorded lecture. All right, I think we're done, which means that we are essentially done with live classes. At this point, you have been through a very, very adventurous journey. A journey through the landscape of artificial intelligence. One of the most important and lucrative technologies available to us at this time. You've learned about some techniques that have real-world implications. You can actually create some AI tools and systems based on what you've learned so far. This is essentially what you're doing in your final project. I hope that I've managed to increase your interest in learning more about artificial intelligence, because what we've covered is not sufficient. Taking an AI course is like wearing a shirt, but this is very important. In my opinion, if you take an AI course, but do not follow up on it by taking a machine learning course, whether be it in the university or from many free online MOOCs, online courses, if you don't take a machine learning course, it's like you're wearing shirts, but not pants. So if you're interested in learning more, if you are interested in becoming an expert in artificial intelligence, your next step in this journey is to learn a lot more about machine learning, which is a topic that we did not and could not cover in this introductory course in artificial intelligence. I'm going to share a number of links to courses that you can follow online to learn about machine learning. Of course, the data science program offers courses in machine learning and deep learning as well. This is not an advertisement. I know many of you are in computer science. Some of you are graduating and don't want to take another course. So my recommendation is, if you are interested, follow one of the MOOCs that I'm going to post on Blackboard. Also, I think you're now able to assess different AI technologies. If you end up in a company, if you end up being the decision maker in a company or a commercial setting that needs to decide between different AI products, you're now able to make an educated judgment. You should be able to evaluate different solutions available to you. And I really hope that I've managed to give you deeper insights into models and theories of human cognition. I really hope that I've managed to pique your interest and curiosity on some philosophical questions, including applied aspects such as how we make decisions. And I want to conclude this lecture and my live classes by telling you that I will always be happy to work with you on research projects or help you with your general questions on artificial intelligence and artificial intelligence techniques. So even after the course is over, do not shy away. If you're interested in learning more about a particular topic, or if you want to work on a particular AI related project, get in touch with me. I'd be happy to help out. Very well. Thank you very much. This is it. I'm going to stop the recording.